All right. All right. Today we're going to put our learning from yesterday with the empirical formula together with molecular formula. Doing molecular formula just really adds one step to the empirical formula. And by the way, the only type of compound that's going to have a molecular formula would be something that is what? The opposite of ionic. Covalent, right? So we're only going to have covalent compounds that have molecular formulas. And the extra information that you'll be given is the molecular mass or the molar mass of the compound. And I'll show you what to do with that at the very end of this problem. So the first, let's go through and do our UKPS stuff, and we'll talk about it in the plan. All right, so the unknown is the molecular formula. So we know the percentage is phosphorus, nitrogen, and chlorine. And the molecular mass of the compound now, what can we solve for if we know the percentages of the elements in the compound? The empirical formula, yes. So that's going to be our first step. Is we're going to do the whole empirical formula thing. So do y'all remember the steps for empirical formula? There are basically two of them: grams to moles, and then divided by the smallest number of moles. There's only going to be one more step, and that's going to be do a comparison, and that's for molecular formula. Sure thing. Yeah, I'm writing really small. All right, so the last step is going to be to compare the empirical formula mass to the molecular mass. And we can't do that until we know what the empirical formula is. So that's pretty much the whole purpose of finding the empirical formula, is so we can compare it to the molecular mass. The next example problem I'm going to give you is just going to have you do this last step, which is compare the empirical formula mass to the molecular mass. All right, so I'll go ahead and start off setting up the solve part of this problem. So when you're given percentages, what do you do with the percentages? Change them to grams. Yeah, just pretend that you have 100 grams of a sample, and then the percentages just become the number of grams. All right, so 26.7 grams of phosphorus, and 12.1 grams of nitrogen, and 61.2 grams of chlorine. I'm going to convert all of those to moles. 30.97 grams of phosphorus and 1 mole of phosphorus. 14 point something, 0.01. And then 35.45. All right, now that we've got our moles, what's the next step? Divide by the smallest. That one still comes out to 1.00, doesn't it? Somewhere around 2. Anybody? 1.99. Is that close enough to 2 to go with 2? Yeah, probably so. Okay. So the empirical formula is P1N1Cl2. Now, so the last step is going to be compare the empirical formula to the molecular mass. So it says that the molecular mass of this compound is supposed to be 695. And we determined that the empirical formula is PnCl2. Now, just a gut check, are those going to add up to 695? Okay, so the molecule must be bigger than just P1N1Cl2. So to figure out how much bigger, let's add up the mass of this compound and see just how much the mass of that is. So the phosphorus is 30.97, and there's just one of them. The nitrogen's 14.01, also just one of them, and then 2 of the chlorine, so 35.45 times 2. And when you add those up, anybody got it? 115.88. That's. Can I get a second on that? I'll just go with the 115.9. Now, what mathematical operation would allow you to figure out how many times this 115.9 will go into 695? What do we need to do to figure that out? Yeah, let's do some division. Okay, so let's compare. So we're going to do 695 divided by 115.9. And I'm guessing 6. 5.99. All right. So great. Now, the question is, what do we do with that? Because they asked us find the molecular formula. So this comparison tells us that the molecular formula is what compared to the empirical formula? 6 times bigger. That's right. So what would how many P's, N's, and Cl's should I have in the molecular formula? P6, N6, Cl. So basically all I did is I multiplied the empirical formula by that number to get the molecular formula. Okay. So this is like basically one extra step. I mean, it's kind of maybe 2 because you have to add up the mass first, but it's basically one extra step. Do y'all think you could do that? Okay, cool. Let's take a look at this other one that's a lot easier. Okay, I crossed out all of this example, 14, just scratch that. We're going to go back and do something just like that in that 9A example that I told you we were going to skip over. So does everybody have what they need off of this? Do I need to leave that up for a moment?
Yes.
Okay. I'll pause for a second. Yeah. All right, so here's our second example on molecular formula. And this one is a lot easier than the previous one because I'm giving you the empirical formula and the molecular mass. So all we're going to have to do is this last little compare step here. So let's set up our UKPS stuff. The unknown is the molecular formula again. The known, we know the empirical formula. And we know the molecular mass. And then the plan, the only part of the plan that we're going to need now, since we already have the empirical formula, so we're going to compare the empirical formula mass to the molecular mass. All right, in order to do that, what's the first thing I need to do? Yeah, add the carbon and the two hydrogens together to get the empirical formula mass. And when you do that, you're going to get something like 14-ish, 14 point something, 14.0 something. Let's see. Yep. All right. And then how did we compare up here? Divide. So we're going to do that again. So 70 divided by 14.026. It's going to be somewhere around 5. Does it actually come out to 5.00? Is it like 4.99? Okay. All right. And what that tells us is that the formula for the molecular formula should be what? C5H10. Y'all got it. Great. All right. So, yeah, C5H10. And I know that's the molecular formula, so I'm going to say so. All right. Oh, I didn't circle the answer up here. There you go. Maybe that makes you feel better. Sometimes I box. Sometimes I circle. Just like, hey, that's what it is. By the way, if you're curious, hey, what is that? That is a ring of pentane. Pent for 5, right? And then carbon makes 4 bonds each. So each of the carbons has 2 hydrogens attached to it. Yay. Okay. Any questions there? All right. When you solve for waters of hydration in a hydrated compound, it's a lot like the empirical formula process. So we're going to go through the same steps as more or less the same steps of empirical formula, except we're not going to separate down into individual elements. The division will be between the ionic compound and then the water. So we're only going to have 2 things where we solve for moles on this. We'll solve for moles of the cobalt 3 oxide, and then we'll also solve for moles of water with the information that they provide us. So let's go through this and set it up. So the unknown, we want to know X waters of hydration. All right, would it make sense to end up with like half of a water molecule or something? No, so this should come out to be a whole number. In practical application in the lab, it's kind of like a round to the nearest whole number and hope you got it right. In problems that you're given, it will come out to be a whole number if you've done it correctly. Let's see, the knowns here. I know the okay, I know the mass with water, and I know the mass without water. Zoom in for y'all. Okay, so one of the things we can do with the information they give us, since we know the mass with water and without, we can subtract to figure out how much water. This is what we're going to do in the alum lab. Is we're going to cook the we're going to cook the water out of the alum to see how many waters of hydration there are. Do this. All right. So the water mass we subtracted to get the cobalt 3 oxide mass is the mass after the water has been cooked out of the sample. And then we're going to convert both of these to moles. All right, so we carried out our calculation. The ionic compound will almost always be lower, and then we'll divide by the smallest. So we solved and found that the ratio is 1 to 1.97, so the value of X is 2.